All right, so let's talk about the test that's coming up. Tests. So this is the midterm exam number 2. So that's basically going to be on, I think it's from like section 2.4 through chapter 3. It's whatever section we left off on in chapter 2. Pretty sure it's 2.4. Then the Wednesday after that is the mastery exam. Basically, what that is, it's all about differentiation. So the way it works essentially is there are 20 derivatives on it. We got 20 functions. You take the derivatives of each of them, and that's it. Sebastian? Through 3, all the way to the end of 3. If you didn't see my announcement, I usually have office hours on Fridays from 2 to 4. I'll be up there from 1 to 4 today. I'll have office hours on Zoom Sunday night from 6 to 8. I think that's, any questions? I think that's all that I got to tell you about the immediate future coming up. Sebastian? They've been on, I put them on campus last weekend. So yeah, there's some practice problems out of the textbook that I put on there. I don't like I said last time, I don't expect you to do absolutely every one of them, but all the ones I put on there are valuable for whatever practice you need. Anything else? All right, so section 2 of chapter 4 is called the mean value theorem. Let's get into it. So let's look at a few things here. So let's say I have a function that's continuous on a closed interval, differentiable on that associated open interval, and the endpoints are equal. So I don't want to draw a picture yet, but think about what that function looks like, and let's answer a few true, false, maybe questions. So let's just take them one at a time. So given the conditions that I'm telling you, is it possible that there are no values on that interval where the derivative is equal 0? Gotta vote for false. So you're saying that's impossible. Oh, so you're saying maybe then there could be values? Yeah. Do there have to be values? The derivative is equal to 0. Yeah, I'm gonna put maybe down because I see some head shakes, I hear some doubts. Maybe this is possible. There are multiple values when the derivative is equal to 0. Can that be true? Must it be true? Also, maybe. Keep in mind, I'm writing down your answers right now. I'm not writing down necessarily the correct ones. There are infinitely many values from the derivative is equal to 0. That one, well, is it possible? Yeah. Let's watch that. There must be some. When I say some, I mean at least one. There must be one place where the derivative is equal to 0. So let's talk about that. So let's say it's impossible. What's an example of a function that would make that work? It's continuous on a closed interval. It's differentiable on that interval. On the open interval, the endpoints are the same, and the derivative is equal to 0 in an infinite number of times. Yeah, a horizontal line, or not x equals 1, but y equals 1. Yeah, a horizontal line would make that work. So we kind of answer it from like this bottom one. And that's the exact opposite of the first one, right? Does there have to be exactly one, or can there be more? There can be more. So that's maybe true. Because could there be exactly one? So I mean, let's. Close interval AB. I know that. So if I have something that looks like that, there's one place where the derivative equals 0, right? So got to have one, right? Could I have more? Could have a lot. What if I have something? That looks like their derivative is never equals 0, right? So if I said that bottom one was true, how did I have this happen? Right. So yeah, I broke my own rules, right? So let me put it it's got to be continuous, got to be differentiable. So this is what the mean value theorem says essentially, is that if you have a function that's continuous on a closed interval, differentiable on that open interval, endpoints are equal, then somewhere the derivative has to equal 0. Are we convinced? I'm not actually going to go through like a really rigorous proof, but are we convinced that has to be true? Ask me questions if not. So we're going to build up to the mean value theorem. For now, let's stick with Rolle's theorem, which is kind of the most specific, kind of limited version of it. But basically, all the same conditions. If f is a closed interval, or f is continuous in a closed interval, differentiable on some open interval, the same one, endpoints are equal, then there has to be a value on the open interval where the derivative is equal 0. Just to be clear, when I say there exists here, and this is something that kind of gets lost in the language here, but there exists. How we doing? Master.
Is that
oh, this thing?
Yeah.
See, I'm going to say, I'll list 2 ways. You can read it as in. That's the most common way it's interpreted, or is an element of. So basically that symbol means there's a thing on the thing in the left of so the C is some member of this larger set, this interval AB. So for example, let's say AB is like -2, 6. Give me a C that works in there.
0.
Yeah, 0 is an element of that thing. Give me a thing that wouldn't make sense. 600 is not an element in that. Anything else? All right, so we want to use that to prove this. I want to prove that this equation, this cubic, has exactly one real root. So let's go back to some theorems we've looked at in the past. One in particular. Because proving that it has exactly one real root is a little bit difficult. So let's do this first. Let's prove that it has roots at all. How could we prove that? No, so when I say a root, basically means I'm saying there's an x value that makes this equation true. So let me draw a graph up in the margins here. And I am not going to graph necessarily this equation, but in fact, it's definitely not going to be this one. But if I were to draw a graph like that, the roots would be here and here. So anywhere the function equals 0. So basically, I'm looking for, I guess the way I wrote this, you could say, like, prove this equation has exactly one real solution. So let's do this first. How would I prove? So prove it has any solution. So how might I prove it has any solution, Sebastian? No, we can't. So let's say I'm not allowed to use a calculator. I don't want to do any of that. How could I like narrow down like, yeah, how can I learn anything about this function? Because I want to know where it equals 0, right? Let's do this. Let's start taking some values. Let's get some data about it. Go ahead. You gotta know what the root is to do that. And the synthetic division is really valuable for once you have a root, like then factoring the polynomial it came from, but in this case, we can't really do that. So let's do this. Let's take these 5x values and figure out what the corresponding f of x values are. That one's easy. If I plug in -2, I get -8 minus 2, that's 11. Minus 3, 1, 9. Did that help at all? I shall tell you, yes, it helps, but why? Why and how? Cameron?
Because there's a sign change in f of x, so we know that it crosses the x-axis at some point, which means it equals.
Okay, so across the x, can we be more specific? Like, if I'm looking for that x value where it happens,
Between -1.
between negative, well, so between 0, so the x value between 0, right? So I know there's a c on this interval, right? 0, 1. Such that f of c equals 0. So, I mean, let's call back to the intermediate value theorem there. Intermediate value theorem only works for certain kinds of functions. Remember what kind of functions that's true for? So this function right here is a polynomial, right? So it's continuous everywhere. Intermediate value theorem only works if your function is continuous. Because otherwise, I can very easily show you a function with no, like, if you don't give me any other restrictions, that has positive values some places, negative values other places, but it's never equal to 0. But polynomial, that's impossible for. So we found that there's some value between 0 and 1 where this function is equal to 0. Now what I want to do is prove that that doesn't happen anywhere else. So basically, here's what I know about this this polynomial so far. Yeah, let's do the derivative, but let me just draw a really simple picture. So between x equals 0 and x equals 1, there's a root, right? And as far as I can tell, the function is negative before that root, positive afterwards. So that's all I know so far. But now what I'm trying to prove is this. I'm trying to prove that it's going to be negative everywhere to the left of that root and positive everywhere to the right of that root. Tongue wants to take a derivative. So prove it has exactly one solution. And if I take a derivative, I get 3x squared plus 1. So what does that derivative tell us? So like, I'll give you a little bit of hint here. Here's what I would like to learn. If I can find out that this function is doing the same thing everywhere, what I mean by that doing the same thing is either increasing everywhere or decreasing everywhere, I think I win, right? Because if it never changes direction, it can't ever come back to the other side.
So that it'll return back.
Yeah. Are we sure this derivative cannot be equal to 0? Yeah, and if I want to drive that point home, I can try to solve it and find out relatively quickly that it can't work. So because the derivative is always positive, this function, basically this is what we're using Rolle's theorem here, but kind of in the opposite direction. Because I proved the derivative cannot be 0, that means I can't have a function where the endpoints are the same, like over any interval. That means I can't ever get back to 0. Basically showing that the derivative is never 0 shows you that the function is it's doing one of two things. Really, we know that it's only doing one thing, but we know it's either increasing everywhere or decreasing everywhere. Can we say for certain which one of those things it is? Right. So, I mean, you can look at the derivative and see that it's always positive, or from that little table we made. Since you know it either has to be increasing or decreasing, we showed that over this little tiny interval it's increasing. That means it's increasing no matter what interval we've got to pick up. It's kind of a deceptively complicated question. I think it's good for looking at that theorem. Jordan? Yes, so we proved that it does have a real root. Oh yeah, we didn't necessarily find it. I mean, it's not like rational. We could solve it algebraically. There is a cubic formula, but I don't remember because it's really, really horrendous, but it exists. So you could find it algebraically, but it was enough to show that it certainly exists. Yeah, what? Focus on that tiny interval. So this is what this little table bought for us is that, and Cameron was right on this sign change in here between x equals 0 and x equals 1. The fact that f of 0 is negative and f of 1 is positive means that somewhere in there, by the intermediate value theorem, basically, I'll just remind you exactly what the intermediate value theorem says. So we have f of 0 was -1, f of 1 was 1. So somewhere in that interval, my function has to take every single value between -1 and 1. Specifically, then we cared about 0. It has to take the value of 0 somewhere too. Fun? Right, so the function increases inside that interval. We needed to look at the derivative to make sure that there were no zeros anywhere else. I mean, there are lots of cubic functions that have 3 real roots. Anything else about this one? All right. So the mean value theorem, basically this is going to be very, very closely related to Rolle's theorem. It's a little bit more versatile. So same thing, f is a continuous function on closed interval AB, differentiable on the open interval AB. What condition did I throw out? Yeah, the endpoints. So for the mean value theorem, the endpoints can be different. But here's what this one says. There has to be a value in that open interval where the derivative is equal to this thing. Let's unpack the thing on the right. What is that? F of B minus F of A? What am I finding there with that? F of B minus F of A over B minus A? That's the slope, right? So if you find the slope over the entire interval, so just like by the time there needs to be some value C. The slope of the is equal to that. And basically, if you just like kind of picture Rolle's theorem, instead of having the 2 endpoints, Rolle's theorem so that those endpoints offset and it'll still work. Any questions before I draw you a picture of this thing? So, yeah, no. Cool. All right. Oh, I wanted to show you something. So, let's think about a closed interval from A to B. Let's actually have the endpoints be different, and we'll draw some strange function like that. So, basically what the mean value theorem says is this. Here's my closed interval AB. I have a function that's continuous on it and differentiable on the open interval. So then what I can do is this. I can draw a straight line from those, and this straight line is equal, so the slope of the straight line is f of B minus f of A over B minus A. So since this function is continuous on that closed interval, differentiable on that open interval, I don't really care what the endpoints are anymore. They can be anything. Mean value theorem says I can say what about this function now? No. So all the points are differential. But what specifically is true about the derivative at certain places?
Has to.
Right. And in this case, like how many points, like do I have 1 point or do I have more? I hear a vote that I have 2. Here's one. If I can draw a line. There's 1, right? I think here's another good one. And I think even further. Just the way I happen to draw this, I would think there were 3. But because of the way the theorem is written, one of those is guaranteed, right? In fact, I can draw you a simple example where and if I were to use the mean value theorem on that, I think I'd find exactly one thing. The mean value theorem guarantees 1. So now that you've seen the words, you've seen the picture, any questions about how this thing works? Are we convinced that it has to be true? All right, let's look at an example. So I got this function here, and it's defined only on this interval 0, 2. I want to find the value of c on this interval. So basically, I have a function that's, why do I know it's continuous on 0, 2? Because what? Right, but so it's defined on the interval, but how do I know it's continuous everywhere on the interval? What kind of a function is that? It's a polynomial. So those are defined and continuous everywhere. So from there, well, I know it's continuous on a closed interval. It's differentiable everywhere. So yeah, including on that open interval. So now I want to try to apply mean value theorem to this. So the mean value theorem tells us this, that somewhere, for some c on 0, 2, actually, the open interval 0, 2, f prime of c is equal to f of b minus f of a over b minus a. So can I find the slope of this function over the interval? Or not the slope of the function, but the slope if I were to join the two endpoints of it. Remember, my a and b in this case are f of 2 and f of 0. So what's f of 2 and what's f of 0? Yep. All right, so then the slope I'm looking at is 6 minus 0 over 2 minus 0, which comes out to be 3. So if I were to draw a secant line from between the endpoints, that slope would be 3, right? So what does that mean about the actual curve itself over that interval? Right. So now the mean value theorem tells us that it must exist. So now that means we can find it, or we at least can start looking for it. So the derivative of this thing is 3x squared minus 1. And I would like to find where that thing equals 3. So from here, I get 3x squared equals 4. X squared equals 4/3. And x equals plus or minus 2 over radical 3. So did I find multiple places where the mean value theorem was true?
Yeah.
I actually only found one. Right, so my interval is 0 to 2, right? So in this case, I can say c is equal to 2 over radical 3, which is about a little more than 1. So yeah, if I were to look at the slope of this curve is 3 at that point. It just mean value theorem does not care. It doesn't tell me anything about that, about whether or not it exists. Any questions here? All right. So drive a car for 4 hours and cover a distance of 280 miles. What can we say about the speed of the car over that? It'll what? Yeah, so I don't really. That's true. That's the thing about it. Take a derivative of. let's just think about, what derivative means in this context. So here, I didn't really give you a function we could like look at and get our hands on. So when we talk about the derivative, what would the derivative represent in this case, in this situation? Yeah, speed, right? So I've told you only that there's a certain amount of time you were driving and a certain amount of distance that you traveled. Does this make sense that when you're driving a car, if I did have a function that modeled that, would it have to be continuous? If you could drive your car in a discontinuous way, that'd be really cool. Just warping between places, which you can't do. So we have to be able to look at that as continuous. Also, the speed of your car can't go from like 0 to anything immediately, right? So that derivative has to exist. There has to be some kind of speed change over time. So I think I fit the criteria of the function being continuous and the function being differential, which means that if I had a function to look at here, I could think about it in terms of mean value theorem. So is there anything at all I can guarantee about the speed of this car over this journey? Eventually go 70 miles an hour, right? How many instances does it go 70 miles an hour? You do know something. And you just know one, right? At least one. So, that's going to sound awkward. For at least one instant, the instantaneous velocity of the car is 70 miles per hour. How else is that figure of 70 miles per hour? How else is that related to this situation? Like, how else could you characterize that over this trip without knowing anything about how I drove between the 2 points? Just kind of overall. Like, what other kind of velocity could I say 70 miles per hour is? Yeah, it's the average speed, right? So the average speed of the car was 70 miles per hour. And that's really what the mean value theorem says, is that if you have a continuous function and a differentiable function, then when you're looking at that closed interval, the average rate of change and the instantaneous rate of change are the same somewhere. Maybe you had your cruise control on and it was the same everywhere. But we do know that it was not exactly. At least one place, the instantaneous speed was 70 miles per hour. Any questions with that? All right. So suppose that f of 0 equals -3 and the derivative is less than or equal to 5 for all values of x. How big can f of 2 possibly be? So let's draw a picture of what we know so far, or what we want to know. So I know that f of 0 is -3. I care about what happens at the point x equals 2. So basically what I want to find is, what is the point, what's the level on that vertical dashed line? Like, what's the highest level I can hit on that vertical dashed line? Where'd you get 7?
It's 5, and then you're moving to.
We okay with that rationale? Yeah, go for it again while I write out the mean value theorem for what we're doing.
Assume that
So I will try to augment what you're saying with the mean value theorem here. And so something I forgot to put in here is that I'm assuming what about f? Assuming f is continuous and also what else? So I'm assuming f is continuous on closed 0, 2 and differentiable on open 0, 2. So I don't know what f of 2 is, do I? But I know what f of 0 is. -3. So because f is continuous and differentiable on this interval, I can use the mean value theorem to tell me something about how this function changes from 0 to 2. So I'm looking for the maximum, right? So even though I was told the derivative is less than or equal to 5, I'm looking for that best case scenario. So I'm just going to say that f prime is equal to 5. So from there, and I think the way that Tal described this made perfect sense. It's totally sound. I'm just basically solving this equation to give us something else to look at. So I'm going to get 13. Oh, no, I'm not. Hold on.
assuming that kind of
So in fact, let me answer this. So we said the maximum, the highest value of f of 2 is 7, right? What has to be true about this function to actually reach 7? It has to be a straight line, right? So let's say up here is this, let's say this right here is 2, 7. If the derivative can never be greater than 5, then the best case scenario is the derivative is equal to 5 the entire way. If the derivative is at any point in that interval less than 5, I won't reach 7. Is there any minimum to what f of 2 could be? Nope. You think of the smallest, like the negative number with the biggest magnitude you want. You could do that. So there's no minimum, but given the conditions I gave you, the maximum is 7. Anything else about this one? All right, so let's look ahead. So I have a function that satisfies the following. So I have a function whose derivative is 0 for all x inside an interval. What can we say about that function? If the derivative is equal to 0 for the entire open interval AB, what can I say about f of x? It's a constant. Does it have to be 0? It can be anything, but just it cannot be variable. How about these two? So I have G and H that are functions that G prime of X equals H prime of X for all X in interval, open interval A, B. Question, Sebastian?
Yeah,
Constant. I'm trying to get in English. Okay, so I have two functions. Do I have to tell you that G and H are continuous? So if two functions are differentiable, then they have to be continuous. So G prime of X equals H prime of X for all X over this interval. What can I say about the relationship between those functions? So they have the same derivative. What does that mean about the functions themselves? They increase and decrease at the same rate. That's true. Can I say any more than that? Can I say this? No, so can I modify this statement to make it something that's necessarily true? Yeah, plus K. So they are not going to be the same function necessarily, but they're going to be different by a constant at the very least. And I think the simplest example I could give you is this: maybe G prime of X equals H prime of X, which equals 5. Could you give me two functions G and H that are different? But this is still true.
yeah, 5x and like 5x plus.
Yeah, two parallel lines are going to have the same derivative, but they'll never be equal anyway. Both of those points make sense? So a couple more theorems to give to you. Basically, just kind of what we just went over. Just kind of wanted to make you reason through them first. If you have some function whose derivative is 0 for all X in an interval, then that function is constant on the closed interval. A very similar idea for the derivatives being equal on an interval. Any questions on either one of these things? All right. Yeah, what's the only way that f of X equals G of X on this interval? That I put this in here. Two ways, Lou. If f of K equals 0, or if f of A equals G of A. So if you can say if the derivatives are equal everywhere and the functions are equal at one point, then they have to be the same everywhere. Sorry, what was that? Yeah. All right, let's look at this thing here. So we have looked at this function before, this x over the absolute value of x. And because I only got a couple minutes, I just want to, let's fast forward to what we've said about this in the past. So this is equal to 1 if x is greater than 0, and it's equal to -1 when x is less than 0. I'll pause there for a bit. Do we remember why that's true? So, I mean, y equals x is just a straight line, that 45-degree angle line. Absolute value of x. Maybe I'll draw both of those real quick. Daniel, do you have a question? So f of x looks like this. So if you think about the ratio between those two things, on the right-hand side of the y-axis, it's pretty easy to see that they're exactly the same. So it's just -1. On the left-hand side of the y-axis, 1 is the exact opposite of the other, so you're going to get that ratio of -1. So from here, think about what we just said with that other theorem was that if the derivative is constant, I don't even know why I wanted to show you this example. Yeah, I take it back. I'm not even sure why I thought that was relevant. I don't see how that fits with the theorem we just talked about. So let me think about that. Maybe otherwise, we'll just take a bunch of sections. So I'll go ahead and stop it there. I have quizzes